Hello everybody, this is Dr. Christopher White, and in this video we are going to be looking at earthquakes. Alright, let's get going. So what is an earthquake? Well, the definition of an earthquake is a vibration of earth produced by a rapid release of energy. So obviously, what kind of energy? Well, the energy in question is mechanical energy, and the mechanical energy is released in the form of waves, which we refer to as seismic waves. So the waves will spread out from the site of the disturbance, and they'll travel through the interior of the earth or along the surface of the earth. And the waves will be recorded by an instrument known as a seismograph, and the seismograph will produce something which we refer to as a seismogram. And I'm sure we've all seen seismogram in the movies, you know when there's some kind of disaster about to occur and you see that, something with a needle just go flying up and down really, really quickly. That's a seismogram. So earthquakes are normally associated with faults, and of course faults are normally associated with plate tectonics. So earthquakes are primarily produced when stress builds up along faults over an extended period of time, and then eventually that fault will slip, releasing the stress that's been built up over the extended period. So how do we describe an earthquake? Well, the area, or essentially the place where the earthquake actually occurs is right here, and in this diagram it's called the hypercenter. It's also sometimes called the focus, and that's described as the location where the rupture begins. So the rupture is actually essentially where the movement on the fault actually occurs. So that essentially, the area of the fault that moves during an earthquake is described as the rupture. Now, the point directly above the hypercenter on the surface of the Earth is referred to as the epicenter, which I dare say is a term that you've heard before. So the seismic waves produced by the earthquake will spread out in all directions from the hypercenter, and the seismic waves will be detected by seismic stations, and of course they'll be detected by the seismographs, and of course that will then produce these seismograms that show the waves as they pass through the area. Obviously, the further away that the seismic station is from the hypercenter, the longer the waves will take to get to it, and that's going to become important later on. Okay, so what's the mechanism for an earthquake? Well, the vast majority of earthquakes are generated by movement along faults. And of course, as we know, most faults are associated with plate tectonics. So there's an intimate relation between faults, plate tectonics, and earthquakes. So obviously, the earthquake itself is going to be produced when a fault slips. So when a fault moves. So when this fault moves, it will release, and essentially produce these seismic waves, which we feel as earthquakes. And of course, as you know, we have 4 different varieties of faults. We have normal faults, we have reverse and thrust faults, and we have strike slip faults. All of these faults are capable of producing earthquakes. Now, earthquakes aren't the only method by which, let me try again. Fault movement isn't the only method by which earthquakes can be produced. We can also produce earthquakes via other means. So large landslides will produce earthquakes. Magma movement underground will produce earthquakes. Explosive volcanic eruptions will produce earthquakes. We can also produce earthquakes by landslides underwater, so these so-called turbidity currents. And we can also produce earthquakes through nuclear tests. So one of the ways that we know nuclear tests have gone on is we can actually detect them. And you can see it here. So here's a nuclear test essentially from India, and you can see the slight difference in the patterns of the seismogram. So this is an earthquake here, and this is a nuclear test here. But the vast majority of earthquakes are associated with faults. So here we actually have several seismograms that are essentially related to nuclear tests. In this case, these nuclear tests are from essentially an array of seismographs in Norway. Okay, and these are detecting nuclear tests in North Korea, to apologise. And so you can see we're going from 2006 to 2009, 2013 and 2016. And so what do we have here? Well, we can see this is the first nuclear test, second nuclear test, third nuclear test. You can see the nuclear bombs they have are going from 1 kiloton to 5 kilotons to 10 kilotons. So the nuclear bombs are definitely getting larger. And then on January the 6th, 2016, they tested a bomb which they claimed was a hydrogen bomb. Now, of course, you may know hydrogen bombs are amongst the most, they're arguably the most, deadly and the most powerful of all the nuclear bomb types. And so the North Koreans had claimed it was a hydrogen bomb, so obviously that would produce quite an exceptionally large explosion, exceptionally large amounts of energy, exceptionally large amounts of seismic waves, which would be very, very powerful. And so at the monitoring station in Norway, what did they find? Well, they found the seismogram that was produced was actually smaller than the seismogram that we see here. And so what do we have? Well, it's probable that the nuclear bomb that was tested in January 2016 was actually just a conventional nuclear weapon, and someone was telling a lie. Okay, so what happens before, during, and after an earthquake? Okay, well, in this case, here's our fault. So we have one block on this side and one block on this side. So our fault plane is going to be coming up along here, essentially where this river valley is. So obviously the blocks want to move past each other. But of course, as we've already touched on, it's not a simple process. The fault blocks don't have a nice smooth face. So they're going to try and move past each other, but they can't because of friction. So friction's going to stop them moving past each other because the surfaces are so rough. So what does this mean? Well, this means over time, this block wants to move this way and this block wants to move this way, but it can't. And so the energy that's being put on these blocks to try and push one way and one the other, remember, this energy is tectonic. It doesn't stop. It's constantly being, they're constantly being pushed to move and move and move and move. And so this energy is locked up in the rocks as elastic strain. Now, the classic example of elastic strain is, of course, a ruler. So here I have the ruler. Okay, you might have seen it pop up in a couple of labs. And as I put essentially force onto the ruler, you can see the ruler is bending, it's flexing. Okay, now what's happening is by flexing the ruler, by the ruler flexing, it's essentially storing up the energy that I've put into it by squishing it from both ends. Now, of course, as soon as I let the ruler go, it snaps back to its original shape. This is elastic strain. So elastic strain is a type of strain whereby something will deform and then return back to its original shape. Okay, so these two blocks of rock are trying to move past each other, but they can't. But the forces that are trying to make them move past each other are constantly pushing on. This means over time, more and more energy is building up. And so over time, we see the amount of stress increasing. So stress essentially means energy. Okay, so obviously the more time that stress has to build up, the more energy will be stored in the rocks, and so the bigger the earthquake will be. Now, stress is going to keep building up and up and up and up, but eventually there's going to come a point where the amount of stored up energy, the amount of stored up stress, will be sufficient to overcome friction. Now, at that point, the fault will slip, it will move. And that's the moment when all of this built-up stress is suddenly released in one big event, which we refer to as an earthquake. Now, obviously, when we release that stress, what's going to happen to this graph? Well, obviously, you're going to see the line suddenly plummet back down again. And so, eventually, the slip on the fault is going to stop. Okay. The rocks themselves, now remember, this is elastic strain we're dealing with, so the rocks will return to their original shape. And then the whole process is just going to start again. We're going to see the stress building up and up and up and up and up, and then it will drop down, up, down, up, down. Okay. Now, this is referred to as stick-slip behavior. and this is because the fault sticks, then slips. So this essentially is the basic mechanism of the elastic rebound theory, and this is very important for essentially faults. So when we are looking at it, so rocks on both sides of the fault will be deformed by the tectonic forces. So what we have here is we have a situation where we have one fault block over here and one fault block over here, and this is the fault plane running through here. Okay, now this block wants to go this way and this block wants to go this way. So obviously they want to move past each other, but they can't, because friction is going to stop them. Friction along the fault plane is not going to let them move past each other easily. So what's going to happen is you're going to end up with a situation like this, where essentially this portion of the block of rock is moving northwards. This portion of the block of rock is moving southwards, but this portion here is essentially locked into place by friction. And so you can see it's beginning to warp, essentially. Once again, just like the ruler, the stored up energy is causing the rocks in these areas to literally flex, storing up the energy. And so we see the rocks in these areas beginning to deform, and they, as a result of the energy that's being stored in them. So eventually what's going to happen is slippage will occur at the weak point, and the weak point will be the focus, or otherwise known as the hypercenter. And so when the earthquake actually occurs, all of a sudden the stress in these rocks will be released, and of course remember, friction is now overcome. So all of a sudden this portion of the rock can now suddenly move northwards very, very quickly. The same with this portion of the fault block, which can now move south very, very quickly. And then we end up with a situation like this, where essentially where the road is now split in two. Okay, so this is once again, this is the stick slip behavior. But this diagram, although simplistic, shows you quite nicely what goes on. So although we have two fault blocks trying to move past each other, well, this portion and this portion of the fault block are perfectly capable of moving past each other relatively easily. It's just the friction here along the fault plane that stops this portion of the two fault blocks actually being able to move, and that's where the deformation occurs, and that's where the elastic strain builds up. And eventually slip will occur, and these two portions of the fault block will snap to essentially to the positions where they actually want to be, and eventually you'll end up with something that looks like this. Now, as discussed, of course, this produces the stress diagrams that look like this. So this is stress builds up, then of course we have the earthquake, stress is released, stress builds up, stress is released, and so on and so on and so on. Okay, now of course the point at which the fault will move is sometimes referred to as the fault strength, and that's essentially the point at which friction is overcome. And now an interesting thing to know is that can be given a value if you have enough data. So if essentially you have measurements of a fault plane, and you can actually measure the amount of stress building up, and you know the amount of stress when the earthquake occurs, well, that actually gives you the fault strength, and that's that's the kind of numerical information that geologists can collect, which allows us to try and predict when earthquakes will happen. We failed, but we're trying to predict it. Okay, so how does an earthquake rupture grow? Well, a fault doesn't begin to slip along its entire length at one time. Instead, the earthquake itself will start with a small rupture, which we refer to as the hypercenter, and it will grow out from there. So in this diagram here, you can see here's our fault, one block here, and the earthquake itself will start here. So this is our hypercenter. Okay, so this is where the slip begins, and steadily over time, the amount of slip, the area suffering slip, will begin to increase and increase. Okay, now what this means is the energy released by the earthquake is essentially released in the form of mechanical energy as seismic waves, but it's also released, of course, well, mechanical energy in the form of seismic waves, but also mechanical energy in the method of movement. So, of course, these two blocks are now moving past each other, aren't they? So the mechanical forces are being essentially used to move the rocks as well. Now, obviously, this means that the larger the rupture, the more rocks are being moved, and therefore the more energy essentially is being used up in the process of moving those rocks. So this means as the rupture grows larger, essentially the earthquake begins to lose power because the energy is being expended in actually moving the blocks of rocks past each other. So if we look at earthquakes, well, what do we see? Where are most earthquakes located? Well, it's not really a huge shock. Most earthquakes are associated with convergent plate boundaries. If we look at divergent plate boundaries here, you'll notice that there is a distinct lack of earthquakes. Now that's because obviously plates are moving away from each other. So that means you're not going to have many bits of rock kind of rubbing against each other, grinding against each other, producing earthquakes. So most of the earthquakes you see here associated with divergent plate boundaries are actually the result of magma moving underground. Now, in the case of convergent and strike-slip boundaries, so transform boundaries, we do actually have blocks of rock trying to move past each other. And that is going to produce essentially blocks of rock that get locked into each other and then suddenly release that energy when they move. So convergent and transform boundaries are associated with earthquakes, or should I say larger earthquakes. Now, the thing you'll notice over here is if we look at essentially the San Andreas fault here and the Queen Charlotte fault here, both transform faults, you'll notice that yes, there are plenty of earthquakes along these fault lines here, along these transform boundaries, but they're all shallow. Now let's compare that to convergent plate boundaries. Let's look at South America. Obviously over here we have the Japanese trench over here. We have obviously the Java Trench right here. Okay, we have the Tongan Trench over here. Well, what do we see in these situations? Well, in these ocean-ocean and ocean-continent convergent boundaries, we obviously have a piece of oceanic crust subducting down underneath a piece of continental crust or oceanic crust. So this means that the earthquakes are not only at the surface, but they also happen deeper as the oceanic crust descends into the mantle. So convergent plate boundaries, ocean-ocean and ocean-continent, are associated with both shallow and deep earthquakes. Now, continent-continent collisions, like the Himalayas for instance, you can see they are dominantly associated with relatively shallow earthquakes. And that's simply because nothing's subducting. And if nothing's subducting, then no piece of rock is going deep down underground, so you're not going to get any deep earthquakes occurring. So, that's a relatively simple explanation there. So, divergent plate boundaries, you tend to have small, shallow earthquakes associated with magma movement. Transform plate boundaries, you tend to get relatively large, actually, shallow earthquakes associated with fault movement. And ocean-ocean and ocean-continent convergent boundaries, you tend to get both shallow and deep earthquakes, and they can range between weak and strong. And at continent-continent convergent boundaries, again, you get lots of shallow, strong earthquakes, and of course you don't get the deep ones because nothing is subducting down into the mantle. So here's the same diagram that we saw before, but in this instance, we're marking out just a couple of key regions of earthquake activity. So this is, of course, the Circum-Pacific Belt. We can see it coming around here. Also known as the Ring of Fire, a term that's we used all the way back when we were looking at plate tectonics. So this region is not only associated with lots and lots of volcanic activity due to the nature of the boundary. Of course, it's essentially almost a non-stop convergent boundary all the way around here. Okay, so we not only have the volcanism associated with that convergent boundary, we also have lots of earthquake activity. So these areas are very, very earthquake rich, shall we say. We also, of course, have the Alpine Himalayan belt. Now, that's the result of the collision between Africa and Europe and India and Asia. Now, Africa and Europe, essentially, it's pretty much a continent-continent collision now. And obviously, India and Asia is a continent-continent collision. And so, Alpine Himalayan type earthquakes are associated with continent-continent convergent plate boundaries. And so what we're going to get is we're going to get lots of shallow earthquakes, which can range anywhere between weak and strong. Now, of course, the problem is because these earthquakes are shallow, if you get a strong one, it's going to do lots and lots of damage. So if we just think about why do ocean and ocean continent convergent boundaries actually have these deep earthquakes, well, let's look at this cross-sectional diagram here. So here we can see this is our piece of oceanic crust descending down into the mantle. Now you can see we have three distinct groups of earthquakes. We have essentially the shallow earthquakes. They range between 0 and 69 kilometers in depth. We have the intermediate earthquakes between 70 and 300 kilometers, which is approximately going to be these ones here. And we have the deep earthquakes, which is normally anything in excess of 300 kilometers. So as you can see, there's a bit of a difference between this diagram here and these values here. All right, so just the way it is. Now, obviously, well, what's causing these earthquakes? Well, obviously, at very, very shallow levels, it's the friction. Oh, I do apologize. It's the friction between the piece of overriding crust and the piece of subducting crust. Now that one's relatively straightforward. Now, as our oceanic crust subducts down into the mantle, as you can see, we're getting, quite deep. So what's happening here? Well, in this instance, the earthquakes are going to be caused by a couple of different things. Number one, as this piece of oceanic crust subducts down into the mantle, well, it's going to be under stress, and in some cases it's going to snap. Of course, when your piece of oceanic crust snaps, of course, that's going to produce an earthquake. Some of these earthquakes are also attributable to changes in the mineralogy of the oceanic crust. So as the oceanic crust subducts down, new minerals will form due to metamorphism. And these minerals will sometimes have different volumes. So all of a sudden you'll see the volume of the oceanic crust maybe expand, or the volume, more likely, the volume of your oceanic crust will decrease. And these changes can actually be quite rapid and forceful. And so you'll literally have a piece of oceanic crust that's that big, suddenly become that big. And so that's a very quick change in thickness. And so once again, that's going to release a large amount of seismic activity. So this is essentially, these deep earthquakes are related to these processes. There is, of course, also the friction between the oceanic crust and, of course, the rocks of the mantle as well, when they're in contact with solid rocks. That friction as well will also lead to the formation of earthquakes. So there's quite a few ways we can form these deep earthquakes relatively easily. So now remember, the thing is, though, is as geologists, what we can do is we can use the data we collect to actually work out, how deep these earthquakes actually are. So once again, if we look at this diagram here, we can see quite clearly where our deep earthquakes are located. So ocean continent here, ocean continent here, obviously ocean over here, ocean over here, ocean here, ocean here, and then we have ocean kind of meets ocean continent over here in the Java Trench area. Okay. Oh, and then of course we have the South Sandwich Trench over here, which is ocean. Okay. And we can see those deep earthquakes. In fact, we can see over here, just below Greece, kind of going up into, Albania that way. We have some intermediate earthquakes here. This is representing the last piece of oceanic crust just dropping down into the mantle. Of course, there's no more subduction going on here, and so what we're going to get is we're going to get earthquake activity driven by continent-continent collision as Africa starts to plough into Europe. So as discussed, earthquakes along mid-Atlantic ridges, they're going to be shallow, they're typically going to be quite weak, and they're mostly associated with magma movement. You will get the occasional one as one block of rock moves past another block of rock along a normal fault, but in the grand scale of things, the vast majority of them are going to be magma movement related. So once again, at a convergent plate boundary, we're obviously going to have large amounts of friction right here, which means this area here is going to be very prone to earthquake activity. We're also going to have lots and lots of faults forming within the mountain ranges themselves. So once again, loads of earthquake activity from those faults as well. Then we're going to have our piece of oceanic crust subducting down into the mantle. Now this is a 3D representation of the west coast of South America, so you can see the trench very, very clearly here. So this is the point where our oceanic crust is subducting. So here's our trench right here on this diagram. And so we can see, if we look at it in section, we can see the earthquakes themselves, so shallow, intermediate, and deep. And so this is actually allowing us to track the piece of oceanic crust as it drops down into the mantle, which is pretty cool when you think about it. Now, essentially convergent plate boundaries are associated with both shallow and deep earthquakes, and they're often quite forceful. So in the case of continent-bound earthquakes, obviously we have continent-continent collisions. In this case, you have two pieces of continental crust banging into each other, and of course these pieces of continental crust are going to want to move past one another, and or go over the top of one another, should I say. And this movement of overriding is going to be essentially accommodated by thrust faults. So once again, lots of pushing forces, okay, which is going to lead to lots of earthquake activity. It's going to be quite powerful, but all that earthquake activity is going to be at a relatively shallow level. Now, when it comes to continent-continent divergent plate boundaries, what are we going to see there? Well, once again, lots of shallow earthquakes, most of them due to magma movement, but you will get some earthquakes associated with fault movement along normal faults, because remember, the area is under extension. It's under tension, should I say. It's being extended. And so this means normal faults are going to form, and obviously the blocks of rock will move relative to each other along those normal faults. And that's when these blocks of rock move, that will lead in some cases to earthquakes. Okay, so this is a really good place to stop. So I'm going to stop here for now. Once again, get up, have a walk around, drink some water, tea, coffee, have a quick snack, and then come back for part 2 when you're ready.